my video I'm going to talk about future rover concepts, which is one of the many available topics at the seminar Interplanetary Exploration at the University of Würzburg, which is a course that is held by Professor Michter. So this is the outline for the video and the content that I'm going to present to you. First, we're going to start with the motivation. We're going to talk about some challenges that rovers currently face and that future rover concepts try to solve. Then I'm going to show you 5 of these future rover concepts: bio-inspired rovers, swarm rovers, modular rovers, hybrid rover drone systems, and artificial intelligence rovers. I will talk about each rover independently and will also give you an example of a mission that it is used for. And at last, I'm going to talk about some combination of these 5 rover concepts that can be utilized together to combine the advantages that each of the rover concept gives. And then I'm going to show you my references that I used for the video. Exploring other planets and celestial bodies with rovers presents several significant challenges that must be addressed to enhance mission success and scientific return. Mobility and navigation rough terrain. Rovers often face difficulty navigating rugged landscapes, including sand, rocks, and craters. These obstacles can severely impede movement, particularly on steep or uneven surfaces where traditional wheeled robots struggle. Communication delays. The vast distances between Earth and other planets result in substantial communication delays. This latency makes real-time control and decision-making challenging, complicating mission management and problem solving. Energy supply limitations. Rovers rely on limited energy sources. Solar-powered rovers depend on sufficient solar radiation, which can be inconsistent or unavailable in certain environments, which we will see for the example for the bio-inspired rover. Environmental conditions. Rovers must endure extreme temperatures, high radiation levels, dust storms, and harsh chemical environments. Their design must account for these factors to ensure longevity and functionality. Bandwidth constraints. The bandwidth for data transmission is restricted, limiting the quantity and quality of scientific data that can be sent back to Earth. This constraint impacts the amount of information that can be collected and analyzed. Mechanical and electronic reliability. Over long mission durations, the reliability of mechanical and electronic systems is crucial. Since on-site maintenance or repairs are not possible, rovers must be designed to operate reliably over extended periods of time. Sample collection analysis. Collecting and analyzing samples in the field is complex and requires high-precision instruments. The transportation of all necessary resources from Earth is impractical, necessitating innovative solutions. Future rover concepts try to solve some of these challenges, and we will see 5 of these concepts in the following. First, I'm going to talk about the bio-inspired rovers. The definition for those rovers are rovers that are inspired by natural systems such as insects, birds, mammals, and reptiles in both physical design and behavior. Those rovers are often legged rovers and look like animals from the nature. For example, you will see that the rovers here have a high resemblance with a dog or a spider. Another example of bio-inspired rovers are soft rovers. For example, the soft robotic rover with electrodynamic power scavenging, which is a prime example. Modeled after a squid, this rover features tentacle-like appendages made from soft, flexible materials. It is designed for amphibious exploration of icy moons like Europa and Enceladus, where traditional rovers would struggle. The rover's soft, adaptable structures allow it to navigate through challenging ice-covered environments and even survive in subsurface oceans. This figure shows the mission concept for the soft robotic rover, consisting of the entry, descent, landing on Europa, the surface operation, drilling, underwater deployment, deep dive, and ocean floor operations. After the entry, descent, landing on Europa, the lander will deploy the melt probe to drill through the ice of Europa. Once the rover reaches the subsurface ocean, it performs autonomous scientific operations such as searching for signs of life and analyzing chemical compositions. This approach enables detailed exploration of environments that are otherwise inaccessible for wheeled rovers. The soft robotic rover resembles a squid with tentacle-like structures. The rover architecture is suited for the moons Europa and Enceladus, whose oceans lie beneath a thick layer of ice. The rover can travel where wheeled vehicles are unsuited to the terrain and where solar power and nuclear power are no viable solutions. To show you the power system, how it works under the subsurface ocean, I will show you a short video of NASA.
Essentially, this is a rover with electrodynamic power scavenging, which means it has a tether. So the concept is this: an electromagnetic tether scavenges power from Europa's passage through Jupiter's magnetosphere. It's the relative motion of Jupiter and the moon, Europa, which then induces a current on this tether. We use that electrodynamic tether power to split water molecules into hydrogen and oxygen components. That combustible gas is then directed into a plenum, where it's detonated, and that process produces a shape change in the soft body of this rover. So it's this detonation inside the body that changes the shape and causes it to sort of move its body through the water. The body itself is made out of some kind of silicone or some other kind of polyacrylamide, some other kind of squishy rubbery stuff, and that allows its shape to change in ways that we don't normally see if we're thinking of robotic systems. It turns out that nature is very good at making efficient creatures that swim through the water. Can we learn from nature? Can we create a rover that swims not through high-speed screws or propellers, but instead through very slow motions of its body, and thereby transferring as much as possible the energy that we do have available into locomotion?
So this was a short video showing how the power system and locomotion works on the subsurface ocean of Europa. I will now show you the Swarm Rover, which is one of the most common used future rover concepts and one of the most important. Definition for this rover is the use of several small cooperating rovers that work together to accomplish complex tasks. One example for a Swarm Rover is the Cooperative Autonomous Distributed Robotic Exploration Mission, or short CATRO mission. This mission uses several small autonomous rovers to work cooperatively together. The rovers should each independently be able to explore large areas, and together they should be able to create detailed maps together. For this sake, each rover is equipped with a wireless radio for communication and a stereo camera for mapping. Because saving space in the lander is so important, during launch and trip through space, the rovers are stored in a compact position in a larger lander. After the arrival, the rovers are ejected onto the surface and explore extreme terrain independently without being controlled by the astronauts or engineers on Earth. We will see a video in the following that shows the deployment of the rovers independently. This video shows how the CATRO mission will work. So as you can see, the Swarm rovers are compactly stored in a lander during space travel and are released onto the surface upon arrival. The rovers work independently to explore and map extreme terrains, coordinating through wireless communication to share data and optimize exploration strategies. The Swarm uses a publish-subscriber communication architecture, as you can see in the figure on the left. So the robots, as you saw on the previous video, communicate with each other, and together they share this information back and transmit it to the base station on the lander. The base station then redistributes all the collected data back to the rovers with more detailed information and compiled maps. The next future concept I will be talking about is the modular rover. The definition for those are rovers consisting of different modules that can be exchanged or extended depending on the specific mission requirements. So modular rovers consist of interchangeable modules that can be adapted or expanded based on mission needs. This flexibility allows for diverse mission objectives and efficient use of resources. One example for a future mission that uses the modular rover concept is the European Moon Rover system, or short EMRS, which is a lunar rover system with a modular approach, meaning it's capable of carrying out different missions with different objectives such as excavating and transporting over 200 kilograms of regolith, building an astrophysical observatory on the far side of the Moon, placing scientific instrumentation at the lunar South Pole, or studying the volcanic history. To achieve this, a modular approach has been adopted for the design of the platform, which allows for accommodating different payloads and allocating them in the most advantageous positions for the missions they are going to undertake. For example, having direct access to the lunar surface for the payloads that require it, while also allowing for the relocation of payloads and reconfiguring the rover design itself to complete completely different tasks. This figure shows how the modular rover with 4 payload bays could look like. There's one primary bay, which is the gray bay in the middle of the rover, which is common among all rovers and will hold common avionics, thermal control systems and power components. There are also 2 side bays, which in this case are pink, and the top bay, which is green, all able to hold different payloads. The multi-purpose rover has 4 possible locomotion modes: skid steering, Ackermann turn, grub turn and point turn. Also, the mobility system as a whole allows for a stowed mode, which means retracting the wheels and lowering the suspension, which significantly reduces the space occupied by the rover, which is the main objective because it's really important to save space in the lander. There are multiple ways of how the modular approach can be used to accomplish the different mission objectives. One way is to make a base model of the rover and customizing the payload with interchangeable modules. This drastically reduces the cost of development. So the idea is to construct multiple rovers, with each rover being equipped with different payload for a specific mission. So they use a standard-side interface and modules that can be easily integrated into the rover depending on the specific mission requirements. Therefore, a rover can be quickly prepared for a new mission by adapting only the modules. Another modular approach idea are docked modules. So for this idea, the rover may be equipped with special docking mechanisms that allow additional modules to be docked. So there is the use of robotic arms that allow the rover to change or extend modules autonomously. There could be also landing units that bring additional modules with landers, and then they could be picked up and integrated by the rover. So there's also a cooperation of several rovers that work together, with some rovers specifically designed to transport and install modules. Another future rover concept is the hybrid rover drone system. So one example for such a rover drone system is an entomopter combined with a ground base station. So an entomopter is a bio-inspired flying robot mimicking insect flight mechanisms. It uses flapping wings for propulsion and maneuverability. It's capable of agile and efficient movements in various environments. On the right you can see the combination of the entomopter, which is able to fly away from the base station, and the base station, which is also at the same time a wheeled rover. The entomopter is integrated with the ground rover. It has a deployment mechanism, meaning that it's stored in a compartment within the rover. After exploring the areas that are inaccessible for wheeled rovers, it will return to the rover for recharging and data transfer. There are several advantages of a hybrid system consisting of a wheeled ground rover and a UAV. One is the enhanced mobility because of the combination of ground and aerial capabilities, and the increased efficiency because of the quick aerial surveys complemented by detailed group analysis. There's also improved safety because of the aerial scouting of the UAV to identify and avoid hazards, and the comprehensive exploration because the UAV has access to diverse terrains and detailed scientific data. This video shows how the hybrid rover drone system will work after the landing. So here you can see that the ground rover is deployed and the entomopter is currently stored inside the rover. the Entomopter can also be deployed from the ground-based station and do its own scientific research, while the rover will also do its own research. You can see that the Entomopter can scout the area around the rover and can gather scientific additional data. It's also suited to terrain where the rover can't go, and you can see that the Entomopter is suited for uneven terrain and can conduct scientific research. You will also see here that the Entomopter can fly back. And for going back, it will be able to recharge and exchange data with the base station. The last future rover concept I will present to you is the artificial intelligent rover. Key feature of these rovers are advanced navigation and obstacle avoidance, real-time data analysis and decision making, autonomous scientific experimentation and sampling, and the adaptability to changing environments and mission goals. There are several AI technologies utilized, for example machine learning for pattern recognition and anomaly detection, neural networks for image and sensor data processing, reinforcement learning for decision making and path planning, and natural language processing for communication and command interpretation. This video will show you how artificial intelligence can be used to conduct scientific research. In this case,
Planetary instrument for X-ray lithochemistry, ready to explore Mars. Pixel's job is to zap Martian rocks with X-rays and figure out their chemical makeup. Think of it like a CSI lab, but on another planet. Traditionally, we had to babysit these rovers from Earth. Every time Perseverance wanted to check out a rock, it had to phone home, and we tell it what to do. But with AI, that's ancient history. Now Pixel, armed with AI, can autonomously adjust its position to get the best angle on a rock, even if it's in a tricky spot. Here's where it gets wild. Pixel doesn't just look at rocks, it analyzes them on the fly. It scans a rock, spits out a detailed chemical map, and decides if it's worth a closer look. All without
At last, I want to talk about some future rover combinations that are also possible, because you don't have to use one singular concept alone. You can also combine different concepts to combine the advantages of each system together. So here I have two pictures showing two different possible ways of how future rover concepts can be combined. On the left you can see legged robots exploring as a team, and you can see those are bio-inspired rovers, as you saw on the first chapter with the bio-inspired rovers, where we said that legged rovers are categorized as bio-inspired rovers, but they are also working together in a swarm, and therefore they will be able to accomplish different tasks, way more complex than a single rover can accomplish. On the right you can see a possible rover formation for a Martian swarm exploration. So here you can see that there are deployed multiple rovers that work together in a swarm, and those are hybrid rover drone systems consisting of a ground rover and a UAV for exploration. So here you have the combined advantages of the hybrid rover drone system, which I showed you the video with the Entomopter, and also the advantages of a swarm rover. These are the references I used for my video. As you can see, I used papers for the K-Drill and the EMS mission, and my video was mainly based on the Planetary Rovers Robotic Exploration of the Solar System book, which is a part of the Interplanetary Exploration seminar at the University of Würzburg.